So, hello everybody, we are back again. So, what we are studying the plasma kinetic theory, and therefrom we are studying whether the theory can predict the existence of electrostatic waves in plasma, which are different from electromagnetic waves. These electrostatic waves are having only electric field, and that propagates in the direction of the field only. Now, for that, actually, we have found the dispersion relation, and then we tried to get the form of GVX in the dispersion relation. Um, uh, in the dispersion relation to understand what kind of behavior it can support. So for that we have made some derivation for the function GVX under Maxwellian distribution, and we are trying to find out what are the properties of the GVX in terms of which the dispersion relation appears. And as I told you in the this GVX, this is having one electron terms also, which is missing over here, and that is actually appearing over here. This is the GVX. So this electron terms is also there apart from the term that is appearing here, and we are considering the total this distribution function GVX, which is having one electron part, this one, and one ion parts. So we finally get the ultimate form of GVX as Me by Mi, 1 by root 2 pi of Vi exponential of minus Vx square by twice Vi square plus 1 by root 2 pi Ve, and then exponential of minus Vx square by twice Ve square. So it is having one ion term, this left side one, and this one is the electron term. Now you can see that the Vi is at the denominator, and you must understand two things over here. One is your omega by k, that is the phase velocity of that electrostatic wave, and the other one is the speed of the particles inside the plasma. So the wave is propagating with some speed, and the particles inside the plasma, they are moving at some other speed, and this Vi and Ve are the thermal speed of electrons and ions. So this is for the ions and this is for the electrons. So you see that there is a distribution of this Vx, there is a distribution of this Vx, and this Vx can be high as well as low, and all over there is certain kind of distribution. And when Vx is small, you see over here, when Vx is small at this location kind of thing, then what you will have actually, then you will get that this term is very small, it is 1 minus, this is giving you almost 1, and then this Vi term, when it is small, it will just blow up, okay. But when your Vx is very high, then this term actually small, and this Ve, usually V is very high compared to this ions. Electron velocity is much higher than the ion velocity. So when Vx is high, then basically this term dominates the electron contribution. But when Vx is small, then this term is it is very small, then this term also exhibits its presence. And the other thing is that you can see over here that it is having a coefficient Me by Mi, and that ratio is very small because mass of electron is small and mass of ion is quite high. So together existence of this term is felt only when your Vx is very close to 0. So this term blows up over here and looks like a cap over this distribution, and otherwise this term actually dominates most of the region. So apart from this very small region close to Vx equal to 0, rest of the region is basically dominated by the your this thing electron term, this term, the second term in this expression. So the other property that we are talking about is Vx is it is symmetric about your Vx equal to 0. So this side and that side they are same. It is obvious because of this exponential of minus Vx square by twice V square form. And then because of this, the function will dominate when ion terms will dominate when your this Vx goes to 0. Because of this thing, Vi is much less than Ve, and central hump is because of that. When Vx itself is very high, ion function contributes minimally and Ve controls the overall behavior, as I have already told you. Now, several interesting properties of this function is integral of gvx dvx is 1. Then gvx into vx into dvx is equal to 0. This is quite understandable because this is a gvx is a symmetric function, and when you multiply with some vx, it becomes an asymmetric, and when you integrate over the whole range, this gives you a 0 value. But when you go for integrating gvx into vx square into dvx, then it results in v square plus vi square. This is some properties which I will actually derive in some of the slides that will come up. So here the properties that integral of gvx dvx is 1. So when this kind of situation arises, you know that gvx is nothing but the probability. When you integrate over the whole vx space, this gives you 1. So gvx gives the probability of finding the particle in vx and vx plus dvx. So how it comes? We write at minus infinity plus infinity gvx dvx, then we write the expression for gvx as a whole, including the electron and the ion terms. And then because the most of the region, this ion term is negligible, we can just concentrate on this electron term, and we are writing this integration as like this. Then we can substitute the variable like x is equal to vx square by twice v square. If we put that, this one, then dx comes like this. You just see that if we make dx, then it is vx dvx, and 2 cancels, and at the bottom you are getting v square. So how do you do that? Then this vx is there, and this comes in the form of square root. So we can write this dx in terms of dvx as root 2 x to the power half, and then this v square and v cancels, so 1 v is left at the denominator. So dx comes like this one, root 2 of x to the power half, then dvx divided by ve. So when we put this dx over here, we replace dvx by this dx, and then you know that we have substituted this variable x equal to vx square by twice v square. So this directly comes here, and it forms exponential of minus x, and the whole integral, this integral in terms of x appears like this, 1 by root pi x to the power minus half. You can see this x goes this side, so x to the power minus half appears because of that, and this is exponential of minus x because we have chosen the variable like that, and then dvx changed to dx like this. So it is, you know that nothing but this is gamma half, and gamma half, you know, the value is root pi, so it cancels and gives you the value of 1. So this is how integral gvx dpx becomes 1, and naturally this gives the probability of finding the particle within vx and vx plus dvx. Now why integral dvx the gvx, vx and dvx is 0, I told you, because this is an asymmetric function. Now what we are interested in is finding the integral of vx square gvx dvx equal to v square. So if we want to find that, then again we come back over here and we take the expression for electron terms only, and this comes as vx square goes out, then this one 1 by root 2 pi e into exponential of minus vx square by dvx, but this gvx expression, whatever we have used here, again we are using the same functionality, that is x is equal to vx square by twice v square variable, and we are using the same transformation. We are putting it over here, then it is coming, this vx should not be outside, actually it should be inside, this should be inside. By mistake it has been put outside, it should be inside over here. And then what we are getting, actually, if we put these values over here, then v is interchanged, and we are getting in the integrand vx square, this vx square is there, and then twice v square, and then exponential of this thing, because there was only one v and we have put v square over here, so we have taken one v out. So we are getting now the same variable here and here, so we can write it as x exponential of minus x, and then we are replacing dvx with your this dx terms, and it's coming over here, and then it is coming root 2, and this root 2 and this root 2 actually cancels, and what we are getting is integral of x to the power half exponential of minus x and then dx. Okay, so this is basically nothing but your what you call this gamma half. This is gamma 3 half, actually. So you put that, root pi by 2 comes over here, and then they cancels out and gives you v square. Okay, so here actually this root 2 here, and you know that when we are putting dvx is equal to, this is by root 2, this is 1 root 2 is cancelling, but here this 2 has come over here, and this 2 basically should be because of multiplication of root 2 and root 2. So there is certain issues, I think, and I will, in the next class I will explain this slide, that how there is probably a little bit of mistakes in this root 2 multiplication, because it should go up, and we'll clarify in the next class. This slide we'll discuss again, and this is basically this function appears, this integration appears, and we get 2 by root pi and root pi by 2, so they cancel out each other, and then we get into v square. So that is how actually you get this integral as v square. Now why we are discussing these integrals over here, because in the latter part we will try to investigate high frequency electrostatic waves, and these high frequency electrostatic waves are called Langmuir waves, and we will try to find out the dispersion relation for Langmuir waves. And Langmuir waves are high frequency electrostatic waves, so in that case omega by k, the phase velocity of the wave is much greater than the thermal speed of the electrons. So in those cases actually we call those waves as Langmuir waves. Now what we have, actually the dispersion relation for electrostatic waves is a general expression which we already obtained in our previous class, that 1 plus omega square by k square integration of 1 by omega by k minus vx and dvx, gvx and dvx. So this is the dispersion relation for electrostatic waves as we have seen in our previous classes. So we are using the same expression over here, only the condition is that omega by k is now much greater than VE. And what is the GVX? GVX is having the form 1 by root 2 pi V, because we know that the ion contribution is only limited in the Vx small zone, and we are considering this omega by k equal to Vx, which is much greater than VE. So it is lying far away from here, and there the consideration of this this electron terms, ion terms is no more there. So we can deal with the electron terms alone actually. So what we are doing here is that we are expanding this by integration by parts, and we have got this expression 1 plus omega e square by k square. Then this first term is there, then integration of the second term minus this derivative of the first term, so square you get, and then you integrate of the second term, you get GVX out, and then this the whole term is equal to 0. So what you are getting, one this dVx and GVX, here this GVX vanishes at both, where? At both plus infinity and minus infinity. So if you do this integration, what is left out is only GVX, and the integration is from minus infinity to plus infinity. So it vanishes at both the limits, so this term gives you 0, and what you are left with is 1 minus this omega e square by k square. This comes over here and acts as coefficient of this term, so omega square, and then this is GVX by omega by k minus Vx, and the whole term square, that is equal to 0. So you get the dispersion relation for Langmuir waves, that is the high frequency electrostatic waves, as like this. Now we come here, because this omega by k is much greater than VE, so we can expand this one, in Taylor series. So what we have done here, just simple expansion, and we are getting this, and we are keeping up to third order, So this is the first order term, and then this is the your second order term. So we are keeping up to second order over here, and then we are doing the integration, and that is becoming 0. So what we are getting, 1 minus omega e square by omega square, then this is minus infinity plus infinity, this is coming GVX dVx, and this one is having Vx multiplied GVX dVx, and the last term is having this Vx squared GVX dVx. Now you probably understand why we were bothered about the integrations that we are dealing a little before. So this is the reason. So when you integrate this integral of GVX dVx over the whole range, you know that we already got the value of the integration as 1. So where we did this one, this integral of GVX dVx equal to 1. So we did that, and we have proved how it appeared. Then in this integration, we proved that integration of Vx square GVX dVx, that is equal to V square, and then we will be putting all these values over here. So, and this Vx GVX dVx, because GVX is symmetric and Vx is makes it asymmetric when you multiply by Vx. So this gives you 0 when you integrate over the whole range. Now the thing is that this term is giving you 1, and this term is giving you 0, and this term is giving you VE square. So what you are finally getting out of this? You are getting 1 minus omega e square by omega square minus 3 of k square V square omega square by omega to the power 4. So we come back here, what we are getting over here, this is V square, this one is V square, what I put in the red box, this is giving you V square. So 3 k square, then V square divided by omega square, you are getting from here, and it is already multiplied by this coefficient omega square by omega square. So your omega square will be in the numerator, k square will be in the numerator, v square will be in the numerator for this term, and in the denominator you will have only omega square, and this omega square will be coming, so it will give you omega to the power 4. So now you can understand how these terms are coming over here. We have v square omega square by omega to the power 4. Now we will be doing a little bit of jugglery over here. This is second order term. No? So when we expand it, this is the first order term, this is the second order term. Now what we have done here, this is a second order term. So that its contribution is quite less, and we are doing some approximation only. This is the general expression for the dispersion relation of Langmuir waves, high frequency electrostatic waves. That is true, and we are trying to reach some simplified version of this expression. So for doing that, anyway we are doing approximation, and this term is having less weightage. So if we just neglect this, then what we are getting? 1 minus omega square equal to 0. So omega square is equal to omega square. So this is certain approximation. So if we do that, and we are actually not neglecting this equation, we are only trying to approximate this term. So if we neglect completely, then we are getting omega square equal to omega square. So if we use this approximation over here, then omega square and omega square cancels, and you are left with what? 1 omega square at the bottom, and omega square goes. So what you are left with? 3k square v square divided by omega square. So the final expression is coming like this: 1 minus omega square by omega square minus thrice k square v square by omega square, and which is equal to 0. So what you are getting actually, omega square is equal to omega square plus thrice k square v square. So this is a very, very simplified form, and looking elegant. And you know that what is the form geometrically? If you plot omega and this axis as k, then you are getting this one. So this is omega square, it will contribute, and then you are getting a parabola kind of thing here, and this is how it goes with k actually. So this is the omega equal root 3 by root 3 into v into k line. So this is the linear, and what you are doing, omega square is equal to omega square plus thrice k square v square. So this is the dispersion relation for Langmuir wave when you do some simplification, and the arguments that you have put goes like this. Now another very important consequence of this kinetic theory is that it can explain why the electrostatic waves get damped as it propagates. So Langmuir wave keeps on losing energy as it propagates, and this phenomenon was actually invented by Landau in 1946, and this damping effect is named in his name and is called Landau damping. Now you know that whenever a wave interacts with a particle, if the wave velocity is too high or if it is too low, the particle does not interact effectively. When the particle velocity and the wave velocity, they are very close to each other, they interact very strongly. So the particle with which are having velocity Vx, which is much greater than omega by k, which is the wave velocity, which is greater than omega, those particles will be grabbed by the wave and they will be slowed down. So which are slowed down? The particles, because the electrostatic wave is moving at a slower speed than the particles in the medium, but they are close by. But the only thing is that wave velocity is less than the particle velocity. So in that case, the particles are grabbed by the wave and they are slowed down. So energy of the particles will be transferred to the wave and the wave gains energy in such cases. Now those particles which have velocity which is say less than this phase velocity of the wave omega by k, so wave will grab this particle and they will accelerate them. So in such case what will happen? The energy of the wave is getting transferred to the particles. So particles are accelerated but the wave loses its energy. So wave is damped. So now we have to find out when there is a high frequency electrostatic waves. So then say let us suppose that this is the omega by k where it lies here. So it is the falling edge of the distribution, and then we see that for any point p on this distribution, this gvx gives the probability of finding the particles within Vx and Vx plus dVx, and we see that the number of particles with velocity less than omega by k is more because this slope is like this. So number of particles less than omega by k is more than the number of particles which are having velocity more than omega by k. So this omega by k is the phase velocity, and according to the distribution, number of particles on the left side of this point P is more here. So those are having lower velocity, and on the right hand side, because of the slopey region, the number of particles which are having velocity more than omega by k, they are less. So because of that, actually what we can conclude, the number of particles in such distribution having velocity more than omega by k is less than the number of particles having velocity less than omega by k. Now those particles which are having less than omega by, what they are doing? They are taking energy from the wave and they are making the wave to get damped. On the other hand, those particles which are having higher velocity, they are trying to make the wave accelerated. So they are making the pumping in the energy into the wave. So the wave ultimately what is happening, the number of particles which are draining out the energy from the wave is more because of this distribution than the number of particles which are putting energy into the wave. So as a whole, the wave is always losing the energy. So as I have shown here, so that is how the wave get damped inside the plasma. The electrostatic waves gets damped as it propagates. So what we find from this is a just a phenomenological explanation of how damping occurs inside plasma. Now, is this always the case? There may be sometimes a distribution, modified distribution may occur where instead of damping you can get amplification as well. So we'll discuss about that in the next class, and then we'll actually finish our this kinetic theory model, and we'll enter into our fluid model. So this much now, and we'll be back in the next class. Thank you.